an engineering degree in imaging science in the 90s. And we worked together when he was here. And you really, even being faculty, you really learn to trust the student when he's steering and you're stoking on a tandem bike and your nose is 6 inches from his spine and you're going for about 2 hours, right? And it was 30, it was probably 35 miles. And
we did 50 miles that day.
Yeah.
Average 20 miles an hour.
Yeah, it was something. It really was. So I know Wayne for quite a while. I saw him give a talk based on this a month ago, the local section of the Imaging Science and Technology Society, and surprised him. He didn't know I was coming. And so he said he'd like to speak at RIT, and voila, here he is. So without further ado, I'll turn you over to Wayne Prentice.
Thank you. Okay, if I can find my mouse. There it is. If I can navigate this sideways. All right, and I bring this up, bring the mouse back over here. You know, for all the technical stuff we do, this should be the easy part, right? All right, very good. Yeah, so I'm an image scientist. I worked at Kodak Digital Capture. One of the things they asked me to do was give a more richer background. So I produced this slide, which hopefully gives you way too much background. So I love imaging. I worked my first darkroom when I was 13. My dad pulled out a box of chemicals and developed my first picture. In my high school, I was photography yearbook editor. Like Roger said, I got a BSEE from Clarkson, and my first job was fixing X-ray equipment here in Rochester. It was the recession. I won't say what year it was, 83. And there wasn't much work out there for especially guys with a cum like mine. So I worked on X-ray equipment, ultrasound, gamma cameras, and then MRIs were a brand new thing. And the old guys were saying that the management was looking for someone to take over the MRI new stuff. And they're like, that sounds like a lot of work. And I'm like, I'd love to do it. It's like, you're brand new out of college. We want somebody who has more maturity, more experience. Well, all the old guys said no. I said yes, and it was a great opportunity. It was a brand new technology. I put the MRI over in Strong in 1984. It was the first high field strength clinical magnet in the U.S. Back then. During that time, I met Dr. Joe Honak, who was doing research there. And he said, you should come to RIT and get a master's degree in image science. I couldn't think of a reason to say no, so I did. And I got that back around the time of the first USB camera. So I left GE, joined Kodak, became a software architect, and I worked on digital cameras and was part of the team when we made the very first USB device, which happened to be, back in the days, that's what a webcam looked like. After that, I moved over to the advanced development group. CMOS sensors were brand new. And so I worked in a group whose job was to create IP, patent things, and play with toys. Did that for a number of years. And then it generalized into something more. Instead of doing what we can do with sensors, what can we do with camera and camera systems? I joined the Image Easy Share software team. At the time, I had 24 million installed base. I wrote the image editor and the raw editor for that product. We had a cell phone product. Kodak realized that consumer space digital cameras had limited lifetime. They got in with Motorola, and we built the ZN5, which was supposed to be one of many. It was described as a great camera, lousy cell phone. So at least we did our part. After that, I became the manager of the image science group at Kodak for digital cameras, responsible for new technology, for image science testing, image quality testing, audio testing, used to benchmark Kodak cameras against the competitors so we could figure out what part of the business space we want to participate in and compare our performance to competitors' performance. Kodak went bankrupt. It wasn't my fault, I don't think. I moved over to what was called Government Commercial, which was then bought out by Harris, which then merged with L3. If you followed all that, I was a principal investigator for creating a new general image quality model. Worked on, that's a Worldview satellite up there. Also did some system modeling with DeerSig. Um, after, while I was doing that, I was contacted by Zeist. They were starting a digital camera program, and they wanted to create a product. And they didn't have any image scientists. They were optical people. I got a chance to work with them for a number of years. So I was doing consulting and working in a real job. Eventually, I quit the real job because the consulting business was a lot better. So I've been doing consulting ever since, and there's a list of things I've worked on. Oil contamination analysis by looking at particles, and actually the spec is written by a shift in color, a delta E star. I never figured they'd do that. A golf ball machine, which took 1,000 frames per second, and we could measure the size of the golf ball, its spin rate, its spin orientation, and use that to predict where the ball would land. I worked on a drone camera, which had a VR headset. You could look in any direction. And you know the jelloing you get with a CMOS sensor? We used an IMU to see which way the camera was looking, see which line of data was being sampled, and then real-time remap that line while the image was being read out to be in the right part of the image space for intra-image stabilization. And then it worked between frames for inter-image stabilization. So the drone could be flopping around in the breeze, and the headset was just rock solid stable, and you could look in any direction in 360 and see what was going on. Worked really cool. Marine surround view. There's a picture of that in the corner. I've done a lot of HDR camera work. I have a whole separate talk on HDR. It's on YouTube right now. If you guys are interested, I'd be happy to give that. Lots of autonomous vehicles. There are autonomous vehicles everywhere, whether they're lawnmowers, delivery vehicles, forklifts. Of course, you know about cars. In-the-sky cameras, you know what's up with that. Intellectual property analysis. I've done some consulting in that area, and I've been twice an expert witness for Canon on the defense side for patent infringement. And I'm also currently the recording secretary on the local, as Roger said, the Image Science and Technology Council locally. So that's sort of my background, and that's who I am. This talk is a little hard to give because you saw the title. It's myths and things. I'm basically going to say there's a bunch of stuff that people think that they know, and I can tell them they're wrong. And I don't want this to sound like I'm being condescending or arrogant. So let's just say after spending the afternoon and talking with a lot of people here, there are very smart people here. And maybe this talk isn't the most appropriate to this audience, but maybe you'll hear me describe stuff that maybe you thought of in a different way. And maybe I'm being pedantic, maybe I'm twisting words, but hear me out and see if at the end you see these concepts and ideas from a slightly different perspective from the way you've heard them generally described. So we're going to talk about areas around image noise, ISO speed, how much does the image sensor noise really impact low light sensitivity, why we really don't want color accuracy for images which for human consumption, and then for machine vision, what is a good aim? And then finally, that perennial question, my mobile phone takes way better pictures than a DSLR. Does it really, and by how much? So to start off, I'd like to go through just a basic laser pointer. I'd like to go through just a basic model of a digital camera, and because this will be sort of the framework for which we speak around. And I'm really going to be centered on what happens at a single pixel. We're not going to worry about larger spatial ideas. And so what happens from a single pixel, of course, is there's some light source that's partially selectively reflected by the spectral reflectance of an object in the scene, or if it's a transmittance filtered. Of course, it's focused, there's an exposure, a blur filter, an IR filter, and then there's a color filter which separates it in the color bands, resulting in ultimately photons being incident on a single pixel. And this is the part we're going to focus on. Photons come in on a single pixel, they shower upon it inside the sensor. That light is converted by the photoelectric effect to electrons. Those electrons are shifted onto a capacitor, which creates a voltage. That voltage is amplified to some convenient input range for an analog digital converter, and that creates the raw data. Now, I know there's much more complex models, but for the purpose of today's talk, that's about as deep as we need to go. So this would be the raw image you get out of your DSLR or whatever. Then that's processed by some internal image signal processor, resulting in an 8-bit image. So that's sort of the lay of the land. If we take this picture here and turn it into a set of signals and their noise, we have the photons arriving, and the photons don't arrive at a regular order. There's photon shot noise, and since photon shot noise is key to this talk and probably one of the least appreciated noise sources, I got a slide just for that. Oh, I gotta turn off the laser pointer to hyperlink. Okay, so photons don't arrive at a constant rate, right? Photons arrive at a random rate, and a random arrival rate is modeled by a Poisson process. You ever hear someone say bad luck comes in threes? You know, you ask them how's business, it comes in clumps. These are all arrival rate kind of processes. If they came at a regular order, right, it wouldn't be random. You could predict when the next one comes. The only way to be random is to not know when the next one's coming. For that to happen, it has to come in clumps. If you could hear, oh, this is probably not going to work. If you could hear, here's the spectrum of the popcorn popping. If you take that not spectrum, the sound trace, if you take this and divide it up into equal increments, you'll see there's some places where you get very few pops. Some places, oops, my laser pointer's not on. Some places where you get very few pops, some places where you get a lot of pops. So the same phenomenology going on for a same fixed interval results in a different number of events. That can be modeled, again, as a Poisson process where the variance is equal to the mean. And just to give it another look, if you had a mean of 1,000 and plotted 100 pixels, so suppose you had a 10 by 10 region, you gave it a uniform light source, just from the photon shot noise, nothing else, not electronic noise, not any other noise in the system, just the arrival rate variation of the photons, you'd get a distribution plus or minus about 100 counts on a mean of 1,000. So photon shot noise is a real noise that happens on the signal before it even arrived to you. I gotta get out of this laser. That's annoying. Okay, so here's our photon shot noise. The signal we get in is based on the number of photons. It has a standard deviation, a variance equal to the mean. There's some quantum efficiency, and that's out of all the photons that arrived, how many turn into an electron? So it's a number less than 1 and greater than 0. And these produce what we call photoelectrons. And we can add to that dark current shot noise. Now, dark current shot noise is like the photons. Electrons percolate into the substrate, out of the substrate into the electron well. And these also arrive as a Poisson process. Fortunately, this is a very low signal unless the sensor is very warm, the pixels are very big, or the exposures are very long. So if you're in astrophotography, it's an issue. If you're imaging cameras in a very hot environment, it's an issue. Or some sensor designs have very large pixels. For most of what I do, we consider that 0. Read noise is the electronics noise, the KTC noise, in the sensor itself. That has 0 mean, so it doesn't shift the level at all, but it does have some level of variation as to the signal. Then there's the system gain, which is again, we saw it in the previous one, that maps the electron signal, the analog signal range to map the input to the A to D. There's also quantization noise, which we added to it, which is due to the fact that we take a continuous signal and move it into a set of discrete steps. So those are the major noise sources. And if we look at the relative sizes, the photon shot noise, an image that's completely black, of course, there's no photon shot noise. If we look at the image, say the electron well, the bucket which holds the electrons, say it fills up to 4,000 electrons, right? If it fills up that high, then the electron shot noise is 64. The dark current noise, like I said, is very small. The read noise, generally speaking, at low gains is 1 to 3 electrons. The thing about if the electron noise was really high, then you wouldn't need such a high fine resolution of your A to D converter, right? If you're, no point in digitizing noise. So that tend to be kept down to a bit or two. And finally, the quantization noise is also very low. So with that kind of model in our head of the relative noise sizes, let's look at our first, oh, sorry, one more background. If we look at the equations, then we end up with the signal is the number of electrons showing up times the quantum efficiency gives us our photoelectrons, and then there's the gain number. The noise is a combination of the photoelectrons and the read noise times the gain number. But here's the important outcome. The SNR, of course, the signal over the noise, they both have common gains, so it turns out that the SNR of the signal that you sample is independent of gain, and that's going to become important later. All right, so first one, image noise is higher in the shadows, isn't in the highlights. Here's a quote from DP Review of why we might think that. The Nikon D7500 images are clean and very detailed up to ISO 800, with just a touch of luminance noise becoming more visible in the shadows as ISO increases. DxO Labs, which is a very respected camera testing site, dynamic range falls rapidly with higher ISO settings, as any analog or digital amplification will increase the noise in the darker areas, making it harder to distinguish among fine levels of contrast. So it's been well established that image noise is higher in the shadows and the highlights. In fact, here's a picture I took with my D7500 at ISO 25,000. And this patch here is plotted over here. And this patch here is over here. And clearly you can see that the 3% patch looks much noisier than 90% patch. So what's my problem with that? Well, the math. Remember, the noise is the combination of the read noise plus the average number of photons arriving. Well, as the photons increase, the noise increases. If I were to measure those plots in the Macbeth color checker, if I measure the standard deviation across here, I can see that the noise increases with reflectance. So it's really not, when we see that, we're not really, shouldn't be saying the noise increases with the shadows. What we really should be saying is the SNR decreases in the shadows. So words, pedantic, why do we care? Well, think about the problem you're trying to solve. If someone says, your problem is your noise is too high, what do you fix? You got one choice, the noise. If the problem is SNR, then your problem is either we have too much noise or not enough signal. Now you got two things you can fix. So it does matter both in the way we talk about it and the way we use it to try to solve a problem related to that. So first myth, noise is lower in the shadows than it is in the highlights. Here's a comment about ISO speed. 3 are correct, 1 is incorrect. First comment is ISO speed determines the sensitivity of the camera. Is it a knob on the camera that changes exposure parameters like shutter speed and aperture based upon scene brightness, and then applies gain necessary to make the picture come out right? Or is it true to say that it determines the amount of photons accumulated during an exposure? Or do I say it's this 10 over HA, where H sub A is the average focal plane illuminance in seconds? Anyone guess? Well, let's ask Canon. Well, when Canon talks about ISO, it says, this is from their instruction manual on the Rebel camera, set the ISO speed to suit the ambient light level, changes the imager's sensitivity to light. The Nikon says the camera sensitivity to light can be adjusted according to the amount of light available. The higher the ISO sensitivity, the less light needed to make an exposure, so on. So any guesses about which one of these is wrong? Well, ISO speed does not increase sensitivity. ISO speed by definition is 10 over H sub A, and that's according to the ISO standard 12232. What ISO speed is it really defines the number of photons per square area weighted by the phototopic efficiency function, because for some obvious reason to somebody, ISO is not based on radiometry, how much power there exists. It's based upon photometry, how bright does it look to a human. It's fair to say that ISO is also a knob that changes exposure parameters and gain. When you say you're imaging in the IR, what is the ISO of a camera in the IR? Well, the photopic efficiency function is 0 there, so H of A is 0. Dividing by 0 is always a bad idea. So it really has no ISO. But it does if you work the camera in a manual mode. If you change ISO, it will change the gain in normalized systems. So I would say it's fair to say that it is a knob that changes gain. So what is sensitivity? I said that ISO doesn't increase sensitivity. Sensitivity mathematically is if there's a bicycle in the scene, what's the probability that I can detect there really is a bicycle in the scene? So that's related directly to SNR. As you increase ISO, you decrease the number of photons. And we know from before, if you decrease the number of photons, you decrease the SNR. Tell me, in what world does decreasing SNR increase sensitivity? So what I'm claiming is ISO does not increase camera sensitivity. By definition, it is the number of photons on the focal plane. And it doesn't matter how those photons got there. It can be a very, very dark scene, and it could have taken an hour to get the photons there. Doesn't matter. It can be a large aperture, small aperture. None of that matters. All it matters is over the window of integration time, how many photons did I collect? That's what ISO is based on. If only I had a sensor that had no read noise, I could image practically in the darkness. At least that's if you read the spec sheets out of sensor manufacturers. They'll all claim that they have really, really great low light performance because they have such low read noise. Well, that kind of makes sense, right? If SNR is the number of photoelectrons divided by the sensor noise, that kind of makes sense. That doesn't. Here's a curve which shows, I'll go over here first. The limiting factor, by the way, is photon shot noise, not sensor read noise. Remember the early slides some time ago? I showed that photon shot noise was about 0 to 64 and read noise was about 2. So let's do a mental thing. Noise adds, in quadrature, it adds in variance. If we take the, remember, the variance is equal to the mean. So we have the mean number of photoelectrons plus the sensor noise squared as a total noise, then said, okay, out of that total noise, what percentage of the noise is due to photon shot noise and what percentage is due to read noise? Here's the plot. You probably can't see it really well. Here's at ISO 100, which is what I call the base ISO, so a gain of 1. At ISO 500,000, at an 18% gray, that's where you get the read noise starting to dominate over the photon shot noise. I don't know how many of you guys image around ISO 500,000. I haven't tried it yet, but the point is, read noise is a really tiny part of that overall noise. Noise is dominated by photon shot noise. And to be honest, it's because of the great work of the people who designed the electronics, designed the sensors. This wasn't always true. The noise levels from the sensors, like I said, tend to be a couple of electrons, which is amazing engineering. And then the people who design the circuit boards they live on have isolated power supplies, done clean electronics, and have made it so that the conversion is very efficient. So as a result of that fine work, it means that for the rest of us, you can pretty much assume that most noise in an image is photon shot noise, except for the very deep shadows, which again you can fix with ISO. Do we want accurate color? I don't know how this comes on the projector, probably pretty good. The image on the left would be an image rendered with optimal color accuracy, minimizing a delta E star between the objects in the scene and the rendering on a monitor. The image on the right is what you typically see out of your digital cameras. And so why are they different? Why don't we like that one better? I've heard it said, and so a lot of the systems I work in have whether it's Qualcomm, NVIDIA, they make their own image signal processor, which converts from raw data to the sRGB space. And if you read their instruction manuals, they always say, well, people just like a snappier picture, you know? There is a real physiological reason for it, two reasons. First one is viewing flare. When you, this color is black and this color is white, right? But this white here is now black over here, right? So in any viewing environment, there's some ambient light which hits the surface you're looking off of and raises the black level. And the other thing is the taking conditions of images are typically brighter than the viewing conditions. So this picture which I had here, those photons aren't coming to you at the same rate as they were when I took the picture, right? That would be a very bright projector. So to counteract for those two things, you have both a perceptual loss of contrast, plus you have a raise in the black level from viewing flare. To counteract that, there's this tone scale that's applied, which provides a toe, which suppresses the shadows, gives a boost in the midtones, and then rolls off the highlights. And as a result, you can recover, which is more of a perceptual match to the scene. So there's a difference between the colorimetric reproduction and the human perception of that reproduction. This, by the way, comes up all the time with my clients who say, I want a camera with a delta E star of 1. It's got to be 1. Anything greater, I can't accept it. You say, I'm sorry, the best I could do was like 2. And they look at it and go, well, that's why it looks so lousy, right? And I go, no, it's because you want this extra thing. And of course, it depends on what the image is used for, as whether or not that's appropriate. So reality, a rendering toe scale has a physiological justification. It's not just an aesthetic. Here's one. A lot of my clients also are into machine vision, and they want me to create pictures for them. And that picture in the upper right is a picture with 3 Macbeth color checkers in it. And of course, you can't see it in that rendering. And if you see the picture on the bottom, you can see the 3rd color checker. The clients say, well, gee, I want some rendering which shows both at the same time, because if I gave that to the top image to my machine vision system, it would never see it. Well, you know, machine vision systems work on information content. It doesn't require a human to visually see it. And I'm pretty sure, if my understanding of information theory is correct, if I have a data set and multiply it by a constant, I haven't increased the information content of the image. Yet if I could take that top image and multiply a constant and get the bottom image, clearly the information of that color checker is clearly in the top image. And so the point is, the goal of rendering images for machine vision is to maximize not the human perception of it, but to maximize the information content. Yeah, my clients have helped me learn a lot. All right, here's the next fun topic. My phone takes better pictures than a digital SLR. And why do we think that? Well, anyone who's ever pulled out their digital SLR, there's someone comes up and says, you know, my mobile phone takes way better pictures than that, and I don't have to carry around that big heavy thing. So let's look at three aspects of it. Let's look at resolution, SNR, dynamic range, and then of course the third variable is generally images from mobile phones are viewed on a mobile phone. So let's see if that has any impact on it. So in terms of resolution, there are 2 things which limit the resolution of a capture device. The first thing is, are you lens limited or are you pixel limited? And here, when light goes through an aperture, it diffracts, and this is a diffraction limit, so it doesn't depend on the quality of the lens. I'm assuming an absolutely perfect lens, no aberrations. So when lens goes through an aperture, it diffracts. The amount it diffracts creates a shape, this airy disc up here, and the size of that airy disc is 1.22. It depends on the wavelength. So I picked the middle, green. I didn't make it multispectral and integrate it from blue to red, because red is fat and diffracts more, and blue is skinny and diffracts less. So we'll just pick a middle number. So that's where I get the 1.22. Oh, already, I'm sorry. 1.22 is in the area discalculation, there's the lambda, and there's the F number. So it depends on the F number and the wavelength. So looking at these two things, the upper limit for an f2 lens is, I'm sorry, for a 2 micron pixel is 250 line pairs per millimeter, and for an f2 lens, it's about 409 line pairs per millimeter. And so the limiting resolution is the bigger of the two, right? So in this case, you're oversampling the blob, and so you're not limited by the sensor resolution, limited by the optics. Over here, the blob is much smaller than a pixel, and so you're limited not by the blob, but by the sensor resolution. And of course, you could be somewhere in between, in which case you have to argue about how much does the Bayer interpolation impact the entire MTF, but it would be something smaller than the blob, but I'm sorry, it'd still be blob limited, but it'd be larger than the sampling. So I'm going to look at 4 devices. A Samsung Galaxy S23, it's a 12 megapixel sensor, f1.8, 1.8 micron pixel. iPhone 15, which I didn't have in hand, but it's a 48 megapixel f1.8, an Nikon D7500. So, in DSLRs, the sensors come in 2 formats. There's the full frame, which is the size of an old 35 millimeter film. Then there's something called a DX format, which is 75% the size. So the D7500 has got the smaller sensor, and the D750 is a full frame. So if we look at the pixel pitch, obviously the Samsung and the iPhone have much smaller pixels, and they get increasingly bigger. The DX has got a smaller pixel than the full frame. And of course, in sensor area, the full frame is significantly way bigger than the 2 mobile phones. So in terms of optical spot size, based upon the F number of the lens, they're all smaller than the pixel size. And so if we look at the functional resolution, because the spot size is smaller than the pixel size, then we're dominated by the pixels. So basically, the mobile phones don't suffer by having such small pixels in this case. The lenses can resolve to that, so we're calling this a draw. The resolution of the cell phones can hold their own to the DSLRs. And here's an example of images. And now there's a 12 megapixel, 21 megapixel, 24 megapixel, and you can see that they all hold their own, regardless of mobile, or the small pixel or big pixel. But now we get into dynamic range and SNR. And of course, dynamic range is the maximum signal you can measure divided by the smallest signal you can measure in the same capture. The electron well capacity increases with the pixel size. So a bigger pixel can hold more electrons, which means you can represent a brighter signal before it saturates. So these are real measurements. So the SNR out of a Samsung S21, what I get here for 18% gray, I think it was 19%. I used Macbeth color checker. Was it 25 something? I didn't have an iPhone, and it's 70 and then 90 for the full frame. So certainly having a bigger pixel helps in SNR. The full well potential, based upon pixel area, you can see that is much larger for the full frame compared to the cell phones. In terms of dynamic range, notice this axis is in stops. So it's a logarithmic axis, and you can see again that the mobile phones are not nearly as good as what you can get with a DSLR. So in terms of dynamic range SNR, there's no doubt that the DSLRs win. So then why do they look so good? Well, you consider the use case. A mobile phone, you tend to take a picture and look at it on the back of the phone. And how big is the screen? It's pretty small. And if you consider the viewing distance from me to the phone and the optical resolution of my eye, the picture that I'm looking at isn't 48 megapixels. It's not 12 megapixels. The best we can see is down to around 2 to 4 megapixels. If you look at an HD monitor, right, an HD monitor is 1920 by 1080, that's 2 megapixels. If you got a nice 4K monitor, that's 8 megapixels. Those are pretty big size monitors, but you're still not seeing per pixel image quality. So when you're looking at even the highest resolution images on your cell phone, they look kind of good because they're really small. And you're not seeing 48 megapixels, you're not seeing 20 megapixels, you're not seeing 12 megapixels, you're only seeing 2 megapixels. And so then the advantage that they had in the beginning, remember, in terms of dynamic range and SNR, the DSLRs were better, but they were par for resolution. Well, the resolution advantage doesn't help you when you're only seeing 2 megapixels of it at a time. And just to put a bow on that, here's a picture I took with my Samsung S21, and it was an ISO 800, 1/4000th of a second. And I tried to match exposure with the full frame. And in this rendering, not so much different. We used to call this pushing in film, and that would be where you basically try to overdevelop it to try to get as much light out as possible. So try to bring up the shadows. And if you look at here, you can see that clearly from an SNR perspective, the DSLR does much better than the Samsung. And also notice here that the Samsung, to match brightness, I pushed it 2 stops, and the Nikon was 4 stops. And the reason why I had to push it more, by the way, it has a much deeper electron well, so it tends to expose lower. And so to bring that back up to an 18 versus a normalized brightness, I had to give it more gain. So clearly there's an SNR advantage of the DSLR. And now here's an enhanced. What I mean by enhanced is I tried to maintain both the shadows and the highlights and render it. And you can clearly see that the DSLR did a much better job of holding the dynamic range than it did than the cell phone. Ooh, I'm doing better on time than I thought. So now I'm going to apologize for talking so quickly. Good luck slowing down, though. That's not been I did this talk a couple of weeks ago, as Roger mentioned, and I was looking at the video this morning before we put it on YouTube, and I was playing it, and I was pretty sure it was playing the wrong speed, because when I listen to me, I sound like, and when I speak, it's just the speed my brain's going. So I apologize for that. Okay, so summary, assuming that it's diffraction limited lens, the lens matched the pixel density on the cell phone, so they're about par with regards to resolution. But in terms of dynamic range, DSLRs have significantly more dynamic range, and if you look at the math, SNR scales with pixel pitch, and DSLRs have significantly more larger pixels. Here's a graph which shows if you were to shoot my Samsung S21 at ISO 100, if I wanted to get the equivalent SNR dynamic range, I would shoot my DX format at ISO, what's this here say, 700, and I could shoot at about 1200 for my full frame. So because the pixels are bigger, you can gather more light, but you're not, I don't want to go into that one. That one gets some complicated thing with focal lengths and things, so I'm going to avoid that one. Mobile phones are increasingly using computational imaging to synthesize a higher dynamic range in SNR, but these tricks usually come at a price, right? When you have motion in the scene, some other things. And the mobile phone display does give an effective resolution of 1 to 2 megapixels, which is part of the reason why we see that they appear to do just as well. So one of the things I was asked to talk about in addition to this was trends. Oh, I'm sorry, I'm getting ahead. So I want to wrap up this part where I talk about trends. So what we've learned is that noise increases with signal, and the noise that we see in the shadows is not because of higher noise, it's because of lower SNR. Gain does not decrease SNR. When you have less photons, you're going to have more noise, but also you have less photons. To renormalize that to display a picture, you have to add gain. Adding that gain does not increase the SNR. adding that gain does not decrease SNR, it keeps it the same. The reason why the noise in the SNR is so much lower is because we started with less photons. So whenever you look at an image now and it's dark, or you're using a high ISO, that noise you're looking at is not because you added more gain, it's because you collected less pixels. Image noise is almost entirely due to photon shot noise under normal imaging. And when I say normal imaging, I'm talking, again, not huge pixels, not really long exposures, not really hot sensors, not astrophotography, not some of the interesting things that are done here in this building. Normal imaging like you would use a mobile phone for, or your DSLR. ISO is not camera sensitivity. ISO is literally the number of photons per unit area collected. Accurate color rendering is not a pretty rendering, but there's a reason why we do that. Mobile phones, best case, are on par for resolution, but lack SNR dynamic range, and DSLRs for that have a 3 to 4 stop advantage. Like I said, mobile phones generally are viewed at lower resolution, and in general, dynamic range scales with pixel area and SNR scales with pixel pitch. Just kind of a rule of thumb to have in your head. So I was asked to talk a little bit about in my industry, what are the trends? Now keep in mind, I'm a consultant, right? So the stuff that I see is stuff that's happened in places like this, then gone to commercialization, and then picked up by people who want to build new products that have problem building those products, and they call me. So I'm a lagging indicator. So what I'm telling you are things which are being used in the industry where I am, which may not be cutting edge compared to where you are. This is not really a capture thing, it's a post-capture thing, but I want to mention it because it's so ubiquitous, is computational imaging. There's a lot of definitions, but I picked the one is computational imaging is computing that which the camera didn't capture. And there's lots of flavors and lots of dimensions. The things that I see it used for, synthetic sharpness, noise cleaning, HDR rendering, and adding, you've seen Photoshop now, right? You've seen the commercial. Put a puppy in that picture, and it puts a puppy in the picture. For the purposes of the kind of imaging I do, that's not interesting or useful. The imaging systems that I work on are used for making decisions, not crashing a car or not driving a lawnmower over some small object. Although one thing I can say here is certainly this adaptive scene lighting may be useful. And this is adaptive scene lighting by the idea of saying, I have a scene, it has a variation in brightness, but I want to see everything in the scene. And by the way, just so you know, maybe obvious, consider a Macbeth color checker. The darkest patch is 3% reflector. The brightest patch is a 90% reflector. So a Macbeth color checker dynamic range is 5 stops, right? 3 into 90 is 30. That's about 32. That's 2 to the 5th. So it's 5 stops at dynamic range, which pretty much fills the dynamic range of sRGB if you do a colorimetric rendering. So when you look at a scene like this, the variation in the dynamic range is not because there's a huge variation in reflectances, it's because there's a huge variation in lighting. And so it's a common technique to say, okay, I'm going to take this scene, I'm going to try to model what I think the lighting distribution is, relight the scene as though the lighting was more uniform, and compute an image. And so the image on the right is probably more useful for human consumption, but it may have some use in a machine vision context. Presuming that machine vision context isn't trying to understand, gain information relative to the distribution of lighting. So machine vision is another huge area, which I'm sure you guys know way more about than I do. But from the purpose of developing digital cameras and deploying digital cameras, a lot of work that I do comes into how to render the pictures coming out. And as I said earlier, the key is to render the images to having maximum information. So how can we white glove the data that we have on the front end to maintain as much information on the back end? That being said, there's two other things we tend to do, and that is there's a labeling process where usually a human observer creates a semantic database which is used to train the images. And that needs to be something that a human can see, where the processing I did about the adaptive scene lighting, bringing up the shadows so the human can see all of the pieces in the scene would be important. So the labeling rendering may be a different rendering than what you use at deploy time or training time. There's another thing that happens is oftentimes customers have got a huge image training set and a testing set, and some were taken, for example, some started as a GoPro, but then I bought an HDR camera. And so then there's a process we can do to homogenize those image assets to make it look like they all came from HDR cameras, to the extent that the SDR camera had the dynamic range. And so homogenizing the data set so that the computer vision system doesn't try to learn the difference between the cameras and use the differences from images to infer scene content allows the networks to be somewhat more efficient. HDR sensors are everywhere. When I mean an HDR sensor is they make sensors now, rather than capturing 10 to 14 stops of scene data, they capture 20 to 24 stops. And they do that by, within a single capture, by either varying the quantum efficiency or varying the integration time. So remember, there's no tricks to be had. The way they extend dynamic range is not by, so dynamic range, right, is the smallest you can detect to the brightest you can detect. It doesn't do anything to make the imagers any more sensitive. What it does is it takes the brightest thing and says, you know what, I'm going to make my sensor less sensitive so it clips later and allows you to extend more dynamic range. So all of these HDR sensors extend the dynamic range on the bright side, do nothing on the dark side. And again, I have a whole talk on this. It turns out that while you can put a sensor on the camera which has that kind of dynamic range, by the time you put an optic on front with the flare from the lens, internal reflections and whatever, and considering the small amount of noise, in the end, the best you get is about 16 stops of dynamic range, which is still better than 10 to 14 stops, but it's not 20 to 24 stops. What this does allow for, though, is a nice technique of having a fixed exposure. So if you're doing video 30 frames per second, you have a fixed aperture, you don't need to change anything, right? You have a fixed aperture, you have a fixed integration time. You can actually expose the image after the fact because you have all this dynamic range. You never overexpose. You want to gather as much light as possible to get the bottom end of the tone scale. So you're collecting the shadows. So you set the camera up for the most sensitive camera, the most integration time, and the largest aperture you can use, add the minimal amount of gain, and then you can normalize the image after the fact, which is nice. Cameras are everywhere, everywhere. And a lot of my business is people deciding, I wanna make an autonomous, actually, like I said, they have lawnmowers, they have sidewalk delivery vehicles, all kinds of things. I've worked on drones, many different kinds of devices, and there's almost no reason not to put a camera somewhere, right? They're fairly cheap. They work fairly well with machine vision being applied to these things. And there's also, rather than doing the entire process of training a machine vision artificial intelligence network, I mean, there are the simple little things of camera looks down at an object, and there's some fiducials, it aligns it, it extracts some features and moves on. So they're very simple applications of that, but it's amazing to me all the places that people are putting cameras and using them for all kinds of applications. More and more, I'm seeing cameras which collect not only scene information, but also are interested in the depth information. So a stereo camera, camera images which are stitched, there's an awful lot of those out there. This device is a 3D 360 camera. So you put on those VR goggles, you can set yourself in the scene, look every direction. Surround view is very popular. You've seen that probably on cars, right? It's a virtual field of view. There's no camera looking down right on top from the camera, from the car. There are cameras around the outside. The actual This is actually a fixed graphic that's pasted on top, and then it creates the sound view around it. Devices like the Meta Quest or the Apple Vision Pro are starting to enable this technology so that there are, right, what's the point of making a 3D environment if no one's there to look at it? Meta has a mission. In fact, here's a quote I found is the metaverse is a vision of what many in the computer industry believes is the next iteration of the internet, a single shared immersive persistent 3D virtual space where humans experience life in ways cannot in the real world. So there's an awful lot of, I think the future is going to be of taking capture devices which do more than capture a flat scene, but capture a 3D world which will be enjoyed with future technology. This GIF here that's running right here is from a company that creates software. You take your drone and you say, I want to model that area. The drone will fly back and forth, capture thousands of pictures, and create models of the area. And they exist for both indoor and outdoor applications. So this VR and augmented reality, and again, a lot of customers too. I worked on a project of, it was for, you set up a camera that set up a soccer field, and it had two cameras, so it saw 180 degrees, and it mapped the whole soccer field, and then all the parents could either watch the game remotely or at least you can make it so it can track your child. So I don't care about those other kids, just mine. So I just want to make a couple statements from a digital camera perspective from the work that I do. And this is pretty much my engineering, my business. Digital camera data, so not aesthetic. I'm not, that's done in another building and people do very good work there. I'm interested in ultimately collecting data, which comes down to megabits to a couple bits, right? Is there a person in front of my car? Where are the lanes of the road? Is this device defective or not? Is there somebody breaking into my building? You know, these megabytes of information get resolved down to a couple of bits, really. And the role of digital camera is to at least measure the portion of the scene which allows you to the highest confidence level determine between the state of, is it this or is it not that? So you don't need to collect everything, but what you collect needs to be able to do that to the highest level of confidence. And so the engineering task that I do in my business is ideally to say, from the output, what are those bits? Then how do we take that space and then project it all the way back to the beginning so we can optimize and spend the least amount of money to get the highest amount of confidence to make those kinds of decisions. And this is done through modeling, calibration, and a lot of empirical testing. But if you were looking for a career in image science, this has been a very lucrative consulting business. So if you want to copy that recipe, I'm retiring soon, so you can have my job. So that's all that I have. Any questions? Thank you. Yes, sir. Can you range? Yes, I avoided the aberrations thing so I could go purely theoretical. But if you include the aberrations, that makes the cell phone. So I came with the conclusion that the DSLR was better than the cell phone, right? The mobile phone. If you include the aberrations, that makes the mobile phone even less. So it makes a stronger argument. And because I could make the argument without including the aberrations, I decided not to include that. And the other thing was I did some testing, so MTF testing to see how much what was the MTF I measured compared to diffraction limited? And the mobile phones I had did remarkably good. I was surprised how well they did. So the aberrations, at least in the one that I tested, I was not, it seemed like I was diffraction limited or very close to it. Yes, sir.
Great talk.
Thank you.
Really enjoyed your blog. As a golfer, I noticed that you consulted work on track golf.
Yes.
And I played some simulators. And it seems to be pretty good. So I wonder if you have any comments on the accuracy. Because I hit a 200-yard drive. Really 200 yards?
Yeah. So let me tell you what was easy. Golf balls are uniform size and they're a sphere, right? So then when you have 1,000 frames per second, you can look at the size of the ball and how it changes, and you can have a pretty good estimate of how much distance it's traveled. So the speed, pretty accurate. The trajectory, we know the distortion of the lens. We can map that out. We can say, okay, I know what the trajectory is, okay? So trajectory and velocity are fairly easy. What was really hard was rotation, right? A ball has dimples on it, and so we tracked mostly the label. If we could see the label, we could see that rotate, and we could use that as an indicator for the spin speed, right? But what was really, really, really hard was the axis of rotation. And of course, that's your slice and your hook. And that was really, really difficult. And so that ended up being, I'll say, lower confidence than the rest by a lot. So if you were saying to me the range was off, I would be surprised by that. If you were telling me the hooks and slices were off, I would expect that. You know, there's probably a marketing reason why they want to err on that side. Yes, sir.
So I was kind of curious, like the future of autonomous driving, will it be more dependent on software improvement?
Okay, so I'm going to give you the old man answer. The old man answer is, as you can see, the thing which, so the real issues are on low light, right, and low contrast. Photon shot noise is hard to win. You can win by bigger sensors, but there's a limit to how big a sensor you're going to spend on that kind of thing. So I think all the gains are going to come on the software side. That's my personal opinion. No other question? Oh, yes, sir.
Well, that's an old man question.
Perfect.
In the olden days, you got slides. There's a big difference between like Kodak and color the way 2D.
Yes.
And at the time, at least, that was attributed to a difference in how different groups heard this. How does that match with what you're saying about the preference?
Yeah. So slides and film, of course, are rendered differently from each other too. And then within the slides, there was a ectochrome, and there was right, and they also had their different looks, right? So, and then if you bought the professional versus the consumer, you also got a different look. So the look, in fact, if you go to Digital Camera World, that curve that I showed you, that was a curve maybe I knew of from a place where I used to work. But if you looked at that same curve from Nikon or Canon, it would be a very different curve. Back in the earlier days, we used to do these, when we compared if our camera was better than the competitors' cameras, we would have a photographer go out and shoot all the cameras in the same market space, right? And we'd put them on a table, and we'd do kind of an assessment out of these three cameras, which picture do I like best, and you kind of walk around the table. And if the marketing people couldn't tell, they were happy that we were in class. It was good, right? And you got to do that a few times. You're like, oh, that's the Sony, that's the Panasonic, that's the Epson. You could tell their looks. Mostly the Sonys tend to be like kind of a bluish thing. I forgot all the details, and of course Kodak had the best look. So I'm not answering your question, but I think there's a look that they're looking for. And that's why that's part of the marketing thing, right? Buy our product because you like our look. Did I answer the question? Well, thank you all very much.